Good morning, everyone. Today we will continue to talk about electric potential. And before we continue to talk about these new things, and I want to review the questions we talked about in last class because due to the time limitation, I didn't talk some details about some problem. Yeah, so let's review those questions in case you have some problems about that. Yeah, okay, let me share my screen. Yeah, firstly, let's talk about this example problem. Yeah, a proton is fired from far away towards the nucleus of an iron atom, which we can model as a sphere containing 25 protons. Yeah, let me uh, draw some important points. Yeah, a sphere. There is a sphere and containing 26 protons. The diameter of the nucleus is this one. And what initial speed does the proton need to just reach to the surface of the nucleus? Assume the nucleus remains at rest. Okay, let's talk about this problem. Actually, for this problem, we know yeah, we treat the nucleus as a sphere with a charge of yeah, there is sphere and there is continue 26 protons. The protons have the charge E. Does it make sense to you? Yeah, so which means the sphere contain 26 E like charges, and it's equal like around it's equal multiple this one. Yeah, it's around uh yeah, it's around this one. This sphere contains what charge? Yeah, this is charge. And then we push like the this proton to a distance of this one. So which means like the center of this sphere, like the distance from the center of this sphere to the distance is around like this one. Yeah, half. Yeah, because this is diameter and the R should be half. That makes sense to you? Okay, and then we know the potential at the surface of this sphere. We can use this equation. Yeah, we talked about in last class. Let us review it. Yeah, this is a potential equation. This one, yeah, does it make sense to you? So we use this equation, and then it will equal around uh yeah, this one. This is the final result, and then we then this is a potential like electrical potential, and for the electrical potential energy is equal what? Is equal QV. Yeah, and we also have this equation. Before let me check it. Check. Yeah, this equation. Yeah, here. Uh, this one. Yeah, this one will be clear. Potential. After that, divide D, and yeah, this one is not very clearly. Let me try to find it for you. Wait me for a moment. Yeah, here. Yeah, like this is transform, but let me try to get a clear. Yeah, here. Yeah, this is a equation for the like electric potential energy. Yes, it is QV. And for now, we know, yeah, yeah, we know like Q, we know like V. This is V, am I right? And then we know Q. Yeah, Q is just E, and so we know like the QV equal uh, multiple like this voltage. And you can see this one actually equal because uh, according to the conservation of energy, it should equal like a kinetic energy. So which means the maximum kinetic energy at the beginning of kinetic energy. So this is the last like a electric potential energy. So which means it equal half. Yeah, you can calculate the speed for the nucleons. Yeah, that makes sense to you? Yeah, if you have any question, just let me know. Okay, let's continue. Yeah, next we talk about the ionization energy. Yeah, we can model an atom as a sphere. Yeah, this is a yeah, this is an atom, and we can like model this as a sphere. Suppose we want to separate an electron from an atom, like here there is a electron, yeah, and from an atom. Removing an electron from an atom leaves a positively charged I behind. That makes sense because firstly it is like a neutral, like the positive and negative is same thing. But you just remove an electron, which means an atom leaves a positive charge. Yeah, because the positive is greater than the negative. Yeah, we can assume that the electron is at the surface of sphere that is equal to the size of the atom. Yeah, we just assume, just assuming. Yeah, maybe the real like situation now that we just assume that the electron is at the surface of a sphere that is equal to the size of atom. It requires energy to separate these two operator charges. Of course, if you want to separate those two opposite charges, it must require energy. Okay, yeah. So this is like a what is so this is a process of ionization, like energy. Yeah. Let's talk about one example, like finding the ionization energy from an atom. Yeah, the radiance of a zinc atom is approximately this one. And what is the energy required to remove an electron from the atom? That is the ionization energy. Yeah, let's talk about the strategy firstly. We can model the atom as a sphere with radiance like this one. Yeah. And removing an electron means moving this negative charge away from a positively charged sphere, the ion the left behind. We can find the difference in potential and use this to compute the charge in potential energy. This is the energy necessary to remove the electron. Yeah. Okay. Yeah. The electron with a negative charge will have a negative potential energy. Yeah. This is obvious. At the surface of the positively charged sphere, removing the electron means removing it to a great distance where V equals 0. Yeah, which means it just separate. Yeah. The electron begins at the surface and ends at a great distance. Yeah. The initial potential. Do you know why it is 0? Yeah. Uh, we just talk about that like just now, like like the V equal what? V equal uh KQR. If the distance is very like far, which means this one is very great, am I right? This means the voltage is very small. If it's great enough, and this will close to 0, that makes sense to you? Yeah. The electron begins at the surface and ends at the great distance. The initial potential at the surface of the sphere is yeah, initial voltage, yeah, equal like VR. The initial potential is the final potential is like we talk about it is zero. So the change in potential is this one. This is a change like initial minus final. Yeah, final is zero and potential initial is VR and equal what? Equal negative VR. Does it make sense to you? Yeah. I think this one is a little something wrong. Yeah, the difference should be f vf minus vi. Yeah, because this is zero, this is VR, so it is negative VR. Yeah, so just pay attention to that. This is not that accurate. Okay. Yeah, VR is a potential now at the surface of the sphere. So it's just a V initial, just use here because it is the potential at the surface of the sphere, which has a radius of the atom and a charge of E. Yeah. So we use this equation K Q R, yeah, to calculate the voltage. This is a convenient tab to use the energy unit EV. Yeah. Moving the electrons through a 10-volt potential difference requires an energy of 10 eV. Yeah. This is a ionization energy. Yeah. Let's assess this result. Our final result 10 EV compares favorably with the mirrored value of 9.4 EV, which gives us confidence in our calculation and in the model underlying it. Yeah, you can check there is a table for the proton, for how removing the protons means like after you move, what is energy required to remove an electron from the atom? That is the ionization energy. Yeah, you can check the table, and this table, the table tell us the Maryland value is 1.5 eV, and what we calculate is 10 eV, so it is near. So which means our result makes sense. Yeah, does this make sense to you? Okay, let's continue. Yeah, we talk about the electric potential of many charges. Before, we just talk about one charge. But here we talk about many charges. Yeah, which means suppose there are many source charges Q1, Q2, the electron potential V at a point in space is sum of the potentials due to each charge. Yeah, you just sum all of them. Yeah. And Ri is the distance from the charge Qi to the point in space where the potential is being calculated. Yeah. Okay. Suppose there are many source charges Q1, Q2. The electric potential V at a point in space is the sum of the potentials due to each charge. Yeah, because we just talked about the electric potential is a simple scalar sum, which is easier to find. As an example, the equipotential map in the figure shows this map. It shows that the potential of an electric dipole is the sum of the potentials of the positive and negative charges. Yeah, you can see here. Here is a positive, here is a negative. Here it will be here the V is positive on this side. Here the V is negative in this side. In the middle, it is the potential is zero. So we call it like the equipotential line. Yeah, and the equipotential line is this green dot line. Yeah, because in this equipotential, which means the potential in this lines is same. That makes sense to you? Okay. Okay, let's talk about one example, like at which point or points is the electric potential zero? Yeah, which means, yeah, you can see here. Here is two, further we speak, there is two, here is one, yeah, because there is two, like proton, there is one electroproton. Yeah, so which means you need to find like a, find the point and the distance, because the distance should be like one differences. Yeah, that makes sense to you, because here the voltage is one differences. Yeah. So and also like you need to find like the like the point should farther from this one and near from this one, because this one is like more than this one. So which means you can see this one like should be zero. Yeah, because this one farther than here, nearer than this, but this one is two, this is one. So which means this one will be like will be like a zero. And also you can see here, this one, no, it's not, because it's near to this one, far to this one, which means this one should be positive. And this one it is near to this one and farther to this one, and this one is like a more, yeah, which means it will be positive. And here you can see it is farther this one and near to this one. Yeah, it seems like seems it might be the right answer, am I right? So and you can see here, it is 1, 2, 3, 4, 5, 6, and it is 1, 2, 3. Yeah, so it is this is six like distance, and this is three distance, and it is like two times. And for the volt, it also two times. Yeah, that makes sense to you. Yeah, so this one is also 0 volt. And here, yeah, you need to let the distance, like this the point to this distance to this distance should be two times, and to this is it should be further. This is nearer. Does it make sense to you? So which means, yeah, it should more than one of these. Yeah, it should be C and D. That makes sense to you? Okay. Let's talk about the other one. Four charges lie on the corners of a square with the size of length A. What is the electric potential at the center of the square? You can see here. Yeah, what is the electric potential at the center of the square, which means here, center of the square. Okay, let's talk about this one. Yeah, it should be, yeah, it should be zero, because you can see from here, like it's just like yeah, the distance here is a, distance here is a, distance here, which means here and to here, yeah, it is the same thing. So which means this one should be zero. Yeah, that makes sense to you. Yeah, based on what we talked about here. Yeah. Let me make it clear. Yeah, you can see as here the equipotential map in the figure shows that the potential of an electric dipole is the sum of potentials of positive and negative charges, and here it should be zero. Oh, sorry, it should be zero. Sorry. Yeah, here it should be zero, because it's like the distance to the positive and negative is the same thing. Yeah, you can see the similar thing here. Yeah, if you want to find the middle point, yeah, it is the distance to the positive and negative is the same thing. Yeah, that is same. That makes sense to you? Okay, let's check the other example, like finding the potential of two charges. What is the electric potential at the point indicated in the figure? Yeah, this one. Okay, the potential at this point is the sum of potential due to each charge. Yeah, the potential is scalar, so we don't need to use angles or find components. Yeah, so what do you just need to know? Just calculate the um, uh, just calculate the potential come from this one and come from this one, and then sum them together. So like the negative charge is 4 centimeter, yeah, from the point at which we are calculating potentials. Yeah, the distance to the positive is the length of hypothesis of the triangle with 3, 4. So which means here is 5. Does it make sense to you? Yeah, it's just a triangle basic information. Okay, so which means the potential at the indicated poles is at 2 plus together. Yeah, so which means yeah, K is the same thing. Yeah, and Q, one is positive 2 and one is negative 1. Yeah, because you can see here. That makes sense to you? Okay. And then, yeah, I don't remember the unit. Yeah, and the one is like a 5 centimeter and the other is 4 centimeter. So the final volt, like electrical potential is 140 volt. For charges and distance, now this magnitudes, this is typical magnitude for the potential. So our result seems reasonable. Yeah. Okay. Yeah, this is the examples we talked like last class. I want to clarify it and let you to understand more about it. And okay, today we will talk about more about electrical potential. Let me share my screen. Okay, let's continue to talk about electric potential. Yeah, and we talk about like in last class, the chapter, the goal for chapter 21 is like to calculate and use the potential, electric potential and electrical potential energy. Yeah, actually we have already talk about more, talk about like much about like the electric potential and electrical potential energy. Yeah, today we will talk about more. Yeah, and some applications. Yeah, this is today's goal. Like firstly, we will review electric potential energy and electric potential. Yeah, and then we will learn how to connect potential and field. Yeah, actually, the potential and the field, they have some relationships. Yeah, we will talk about that. And next, we will understand the electrocardiogram. Actually, this is a very useful application. We will talk about how these things, how electrocardiogram use electric potential and electric potential energy to like successfully like mirror our body's features like that. And then we will study like capacitance and capacitors. Yeah. Finally, we will learn like energy and capacitors. Yeah. Those three like seem some like applications. Yeah, we will talk about. Yeah. Firstly, let's review the electric potential and potential energy. Yeah. We know like the electric like a potential V is created by charges and exists at every point surrounding those charges. Yeah. When a charge Q is brought near these charges, yeah, you can see here there is a yeah, like this kind of charges, yeah, created the electric potential. And when a charge Q, this black dot, is brought near these charges, it acquires an electric potential energy. And this is the electric potential energy. Yeah, how to calculate it? It's Q multiple the voltage. Yeah. For example, here the voltage is negative 100, then it will be Q multiple negative 100 volt. Yeah, here is the 300 volt multiple like Q. Yeah, the similar thing for here. At a point where the other charges have created an electric potential V, energy is conserved for a charged particle in an electric potential. Yeah, we talk about this. Yeah, this is a like a final like a final energy situation, like the kinetic energy plus the electric potential energy equals like initial like kinetic potential plus like a initial electric potential energy. So if we rearrange it this equation like a kf like a minus ki equal what equal qvi minus, yeah, that makes sense to you. So kf minus k like f like final kinetic energy minus the initial kinetic energy, which is delta k, and then vi minus vf, it is negative delta v, because delta v equal what vf minus vi, but here is vi minus vf, so it is negative q delta v. That makes sense to you? Okay. And then this is for the like electric potential and electric potential energy. Yeah, how to calculate it and how to represent it. And here we talk about some sources of potential. Like potential differences, like delta V, are created by a separate charge. Yeah, actually, if you separate charge, like separate the negative and positive, it will have the like electric potential differences. Yeah, two important sources of potential difference are like this one. We usually see it in our real world, a battery, which uses chemical means like to separate charge and produce a potential difference. Yeah, the opposite charges on the plate of a capacitor. Yeah, this is the other one. Like one is battery. Yeah, the other is capacitor. Yeah, the opposite charges on the plates of a capacitor, which create potential differences between the plates. Yeah, and the electrical potential of a point charge. Yeah, we can calculate using this equation. Yeah, this is for point charge Q. Yeah, like V equal K. K is a constant. Yeah, and like for the like a capacitor charge, yeah, there is another like equations. Yeah, you can review it, but it's similar with this one. Yeah, and let's talk about like a connecting potential and fields. Field. Yeah, and you can like review some videos here, like to see like connecting field and the potential. Yeah, but we will not review it in this class. Okay, let's try to connect potential and field. Yeah, source charges create an electric field and an electrical potential around them. Yeah, we talk about this in chapter 20. Yeah, and this like in next class. Yeah, field and potential are clearly linked. We can understand how by considering the work done to move a charge. You can see when a charge is moved along an equipotential, its potential energy doesn't change, yeah, because it's equipotential line, which means the the electric potential is the same thing, yeah, and the potential energy does not change, yeah. So like but what is changed? We will talk about it. Suppose a charge Q, yeah, moves a short distance along one of the potential like surfaces. Yeah, the potential and hence its potential energy are the same at the beginning and the end of its displacement. This means that no work is done in moving the charge. That makes sense to you? Yeah, because the potential energy is same, so the begin at the beginning and the end. Yeah, so the which means like the total like energy equal what K. This is kinetic energy plus potential energy. Am I right? QV. But this one is the same thing. So which means the total is the same, is a constant. So this which means the connected also the same. So there is no work is done. Yeah, this is possible. Actually, maybe some students maybe think it's impossible because you move it, am I right? But this is possible only if the electric field is perpendicular to its motion, so that no work is done in moving the charge. Which means the electric field. This is electric field is perpendicular to its motion. Yeah, this is the motion. If this it has this relationship, which means no work is done in moving the charge. Yeah, this in this situation, like this like no work is done is possible. Yeah, let's continue. That the only way that no work can be done is if electrical field is perpendicular to the equipotential. Yeah, otherwise it is impossible. Yeah, you can see the electric field causes the charge to speed up as it falls toward lower electric potential. Yeah. Okay, the electric field at a point is perpendicular to the equipotential surface at that point. A positive charge speeds up as it moves from higher to lower potential. Yeah, if the motion direction is just like this, yeah, because from the higher potential to the lower potential, you can see here from 10 to, yeah, and a positive charge will speed up, but so this charge will speed up as it moves towards the lower zero equipotential. Yeah, it is obvious. Which means if you move from here to here, which means the potential like electric potential energy decrease. Am I right? Yeah, the key and the potential energy like QV equal constant. If this one is a decrease, which means this one is increase. That makes sense to you? Yeah. So which means the kinetic energy increase, which means speeds up. That makes sense to you? Okay. Let's talk about continue to talk about the work required to move a charge at a constant speed in a direction opposite the electric field. It's this one. Yeah, if you move a charge at a constant speed, but in a direction opposite the electric field, and the work should equal the difference of like electric potential energy. It is equal this one Q delta V. Because the charge moves at a constant speed, the force of a hand moving the charge is equal to that of the electric force. That makes sense to you? Yeah, because a constant there is a constant speed, which means the net force at every point, the net force is zero, which means the force of a hand moving the charge is equal to the that of the equal electric force, and this is work like by hand. Yeah, this is the force, and this is force by hand. This is the distance, and this is the electric force, and like distance. Yeah, that makes sense to you. Okay, compare these equations. We find that the strength of electric field is this one. Yeah, because you can see here, Q E D equal F and D equal what? Equal Q delta V. Yeah, because this equal this one and this one equal this one. That makes sense to you. Yeah, so which means QED equal Q delta V. So which means yeah, E equal delta V divided D. Yeah, so which means the strength of the electric field, yeah, like equal this one. That makes sense to you. Yeah, you also can see a video about this, but I will not play it here to save time. Okay, let's continue. Yeah, this is how this equation obtained. Yeah, electric field strength in terms of the potential difference delta V and between the two equipotential surface a distance d apart. Okay, let's continue to talk about the magnitude of E. Yeah, this is like a electric field. Yeah, the magnitude of electric field is determined by considering the work required to move the charge at a constant speed through a displacement like that is directed opposite like a electric field. Yeah, because you can see we know E equal what? Delta V divide D, am I right? Yeah, we have already talk about that. Delta V divided D. Yeah, which means like the magnitude E, yeah, is determined by considering the work required to move the charge. Yeah, we talk about that here. Yeah, this is the work, and this is the equation for that. And at a constant speed through a displacement that is directed opposite E. Yeah, you can see here. If you use hand to push it to the hair like potential hair potential, and the displacement is directed, yeah, the opposite E. That makes sense to you. And the magnitude is determined by the work. Yeah, that makes sense to you. Okay. And let's talk about the geometry of potential and field. You can see here, E, like electric field, is everywhere perpendicular to the equipotential surface. Actually, yeah, the E is everywhere, and the direction is perpendicular to the equipotential surfaces. And this is lower potential, this is higher potential. And yeah, this is the direction of the decreasing potential. Yeah, like because this is lower, this is higher. And the electric field points downhill in the direction of decreasing V. Yeah, it should like points downhill in the direction of decreasing V. And the field strength is inversely proportional to the space d between the potential surface. Yeah, you can see here, because E equal what? Delta V divided D. Yeah, which means the field, this field strength is inversely proportional to the space d between the potential surfaces. That makes sense to you, because this one, if you decrease this one, and this one will increase, it will increase this one, this will decrease. Yeah, okay. And let's talk about one question. Yeah, a proton starts from rest at point A, it then accelerates past point B. Yeah, like this one. And the proton's kinetic energy at point B is what? Yeah, that makes sense. Do you know what is this one? Yeah, because you can see the question tell us like a proton starts from rest at point A, which means at point A it only has the electric potential energy, and electric potential energy, and there is no like a kinetic energy because it is rest. That makes sense to you. So which means it is only like have Q V. I'm right, and this is a proton. So which means it is E 200 205 and 5 eV in point B. This is the electric potential energy. And to the accelerates past point B, and which means it will like the here the electric potential energy will become QV. Am I right? It will be 150 eV. So which means this one, the difference between this one will be the kinetic energy change. That makes sense to you. Yeah, because the electric potential energy will transfer to the kinetic energy. So what's the difference? It is 100 eV. Am I right? Yeah. So actually, you can also use this equation. Yeah, this equation to calculate it. Yeah, which means the kinetic energy equal what? Equal delta. Delta like electrical potential energy equal what? Q delta V. Yeah, Q is like E, am I right? And delta V equal 100, so 100 EV. Yeah, it's the same thing. So the answer should be 100 EV. That makes sense to you. Okay, let's talk about the other let's continue to talk about connecting potential and the field. Yeah, you can see below are three important arrangement of charges. Yeah, this is just a one single charge, one single positive point charge. This is the electric dipole. Yeah, like one proton and one electron, and they are same. And the next one is the parallel plate capacitors. Yeah, capacitor. Yeah, those are three important arrangements of charges. Both electric field lengths and potentials are shown. You can see for a point charge, the this green one is equipotential line, and you can see the electric field is perpendicular to the electric equipotential lines. Yeah, you can see field lines are everywhere perpendicular to equipotentials. Yeah, and you can see here the electrical field is stronger where equipotential are closer together. Yeah, that makes sense to you. Yeah, which means the relationship of the electric field is stronger where the equipotentials are close together. Okay, let's see the electrical dipole. Actually, it has a similar thing. Yeah, you can see the field length. This the red length is the field length are everywhere and perpendicular to equipotentials. Yeah, that makes sense to you. And also the electric field is stronger where equipotentials are close together. Yeah, those two are same with the point charge. And the new thing is you can see here the field length. The field length point from here to lower potential. Yeah, you can see because the point of charge is only one, so there is no like a higher on there is no like a actually it also I think this one also apply. Sorry, I just make a mistake. This one also applies to the point charge because the field length, you can see the red length point from higher to lower potential. This is a lower higher potential. This is lower potential. You can see it is because it is loose. Yeah, and the similar thing to the electric dipole. Yeah, the field length point. Yeah, point from the higher potential to the lower potential. You can see from here to the lower, from here to the lower, from here to the lower. It doesn't make sense to you. Yeah, because for the negative, the potential is negative. It will be like smaller than zero. So which means it will be lower than negative is lower than zero, like that in this definition. Doesn't make sense to you. Okay, like for parallel plate capacitor. Yeah, the field length point from here to lower potential. Yeah, it's a similar thing to the lower potential. And for the capacitor, the field is uniform. Yeah, and so the equipotential space is constant. Yeah, you can see. Yeah, because the field is uniform. Everywhere is the same. Everywhere is the same. So the equipotential space is constant. It is constant. Yeah, that makes sense to you. Yeah. Okay, let's continue to talk about. Okay, let's check this question. Like as a middle point between these two equal but opposite charges, which one is right? Yeah, actually we talk about this. Like for this two, there is two different charge source. One is positive, the other is negative. And for this one, the voltage should be 0. Yeah, because you can because yeah, we talk about this. Let me show you. Here. Oh, we talk about like in last class just now, like yeah, yeah, just like in last class, yeah, and for oh, I think the inlet is not right, is not good, yeah, and for this point, since here is 1 voltage, here is a negative 1 voltage, here it should be like the zero voltage here. Sorry, I don't. Yeah, here should be 0. And for the like electric field, you know, like it should be like it should point from positive to negative. Yeah, so which means it should point to this one, point this one, point this one, point this one, point this one. Yeah, yeah, yeah. From this one, from this one. Yeah, which means in this point, and the electrical field should point right. Yeah, this direction. Does it make sense to you? And the voltage here, yeah, because here is positive 1 volt, negative 1 volt. So here there should be 0 volt in the middle. Yeah, so the right answer should be D. Yeah, you didn't see the right answer. That's not right. Yeah, okay. Yeah, any question, just let me know. Let's talk about the other one. And a particle follows a trajectory here from I to F, and from initial point I, position I to final position F. The potential difference delta V is what? Yeah, I think this one is obvious. Like the delta V equal what? Delta V equal VF minus VI, and VF is what? Yeah, because this is a equipotential like a line, which means in this line the voltage is the same, and it's this one, so it is negative, and in this it is a similar thing. It is 0 volt, so it is 0 volt, and it is negative 50 volt. Yeah, so which means that it is negative 50 volt in D. That makes sense to you, because yeah, this we need to use this equation, and the difference, the potential difference is independent of the path. Yeah, that makes sense to you. Even if your the path is just like this, yeah, and it also like 15 like a 15 volt difference. Okay. Okay, let's talk about this question. Like, which set of equipotential surfaces matches this electric field? And you can see here, this is the electric field, and we know like the equipotential surface should be perpendicular to the electric field. So yeah, those five seems also right. And you can see here, we know like the electric field, it should be from the positive to the negative. Am I right? So which means here this it should be positive, and to that one will be decrease. Does it make sense to you? So which means this one, and this one is right. Those three, yeah. And then we know like we also know like here which one? Which one? I think the inlet is not good today. And here we know like the electric field is stronger where potential are close together. So which means here in this question here you can see in this location it is stronger, which means the equipotential lines will be closer. So which means this one is closer. That makes sense to you. So the right answer should be C. Yeah, that makes sense to you. Okay, yeah. Okay, let's talk about this example problem. this example problem, what are the magnitude and direction of the electric field at this dot? Yeah, and this is the green line is the equipotential line, and you know that the positive charges slide downhill. Yeah, so from high potential to the low potential, the electric field point in that direction. Yeah, it should be for the electric field. It should from the positive to negative. We have already talked about that. Yeah, and from so to the left. Yeah, the direction to the left. Yeah, and then let's talk about the magnitude. Actually, the magnitude is we talk about that. Yeah, in the beginning here. Yeah, what is the electric field equal this one? E equal delta V divided D. So let's go back to this. Oh, sorry, go back to this question. Yeah, so here E equal divide divide V D, and D here D is what equal 1 centimeter, am I right? Delta V equal what 100. Yeah, from here to here 100, which means it should be 100 V divided 1 meter. This one. That makes sense to you? Okay. Yeah, this is I just give you the hint. You can calculate it by yourself. Okay, let's talk about conductor in electrostatic equilibrium. Yeah, there are the 4 important properties about conductors in electrostatic equilibrium. We already knew. Actually, we talked about this in last class for the conductor. Yeah, the first one is any excess charge is on the surface. Yeah, and the electric field inside is 0. Yeah, we talk about this. And the external like electric field is perpendicular to the surface. Yeah, and the field strength is largest at sharp corners. Yeah, do you remember this one? This one, and all the like field strength is here. Yeah, and the fifth important property we can add now, like the entire conductor is at the same potential. At thus, the surface is an equipotential surface. For example, here is a conductor, and in the surface, and it has the same potential, and the surface is an equipotential surface. Yeah, this is like we can add in this class. Okay, let's talk about more about this. You can see inside a conductor, the electric field is 0. The electric field is 0. Therefore, no work can be done on a charge, and so there can be no difference in potential between 2 points. The difference potential also 0. And any 2 points inside a conductor in electrostatic equilibrium are at the same potential. That makes sense to you, because for the point 1, point 2, the difference electrical potential is 0, which means that the electrical potential point 1, point 2 is the same thing. Yeah, so this is like any 2 points inside a conductor is in like a electrostatic equilibrium. Yeah, that makes sense to you. Okay, like properties of a conductor in electrostatic equilibrium. Yeah, we talk about just now. Like all excess charge is on the surface. Yeah, and the electric field inside is 0, and the external external like electric field is perpendicular to the surface. Yeah, and the electric field strength is largest at the sharp corners. The entire conductor is at the same potential, so its surface is in an equipotential line. Yeah, that makes sense to you. Yeah, since we have already talked about that, because any point, like any 2 point inside the conductor in like electrostatic equilibrium at the same like potential, which means inside the conductor, all the points is in the same potential, like the same potential, which means in the surface, yeah, there are same potential. Yeah, that makes sense to you. Okay, let's continue. Yeah, let's talk about the electrocardiogram. Yeah, this is a very important applications for we should learn. Okay, let's continue to talk about it. Okay, let's talk about electrocardiogram. Yeah. For the electrocardiogram, we need to know something about that. The first one is the electrical activity of cardiac muscle cells makes the beating heart an electric dipole. Yeah, actually, I think we have already talked about this. The electric activity of cardiac muscle cells makes the beating heart an electric dipole. Yeah, you can review what we talk about in last class. Also, we will talk about more later. Yeah, a resting nerve cell is polarized, and the outside is positive and the inside is negative. Initially, all muscle cells in the heart are polarized until an electrical impulse from the heart triggers the cells to depolarize. Moving arms, moving arms through the cell wall until the outside becomes negative. This causes the muscle to contract. Yeah, this is why our heart beat like that. Yeah, the depolarization of one cell triggers a wave of depolarization to spread across the tissue of the heart. At any instant, a boundary divides the negative charges of depolarized cells from the positive charges of cells that have not yet depolarized in the heart. The separation of charges creates an electric dipole and produces a dipole electric field and a potential. And we will talk about more. You can see there is a heart diagram. Yeah, the boundary between here is the boundary. Yeah, between polarized and developed between polarized and depolarized cells sweeps rapidly across the atria. Yeah, you can see this one. This part is a depolarized cells, and this one is a dipole moment. Yeah, because here is a positive, here is negative, and here this part it is polarized cells. Yeah, at the boundary, there is a charge separation. This creates an electric dipole and an associated dipole moment. Yeah, that makes sense to you. Okay. And then you can see because because there is a electric dipole, so this electric dipole form like a potential electrical potential and electric field. Yeah, here is a positive potential, here is negative potential. Yeah, because you can see here is positive, this half is positive, this half is negative. Yeah, and form this electric potential and electric field. And yeah, you can see a measurement of electrical potential of the heart is an invaluable diagnostic tool. The potential difference in potential is measured between several pairs of electrodes. Yeah, we will talk about later. A chart of the potential differences is electrocardiogram, also called an ECG or an EKG. Yeah, this is the short name for that. With each heartbeat, the wave of depolarization moves across the heart muscle. The dipole moment of the heart changes magnitude and direction. Yeah, this is, you can see if you do some body exam, you will you can see the doctor use electrocardiogram and to measure your heartbeat rate and to see if your heart works normal. Yeah, runs normal like that. You can see you will the nurse or the doctor will put many electrodes are attached to the torso, yeah, like this uh, vital ones, and records the potential differences between various pairs of electrodes, allows the doctor to analyze the heart's condition. Yeah, which means, yeah, you can see if you this depolarization and polarization and depolarization, and then there will be a potential difference. And this potential differences between various pairs of electrodes allow the doctor to analyze the heart's condition. Yeah, does it make sense to you? Okay, you can see here, for example, this is the position A, and there are two different electrodes. Yeah, electrode one, electrode two. This is one, this is two, and you can see, and there will be like electric potential difference. Yeah, V2 divided V1. Yeah, this is the record of the potential difference between the two electrodes. Is the electrocardiogram. The potential difference at A, B, C correspond to, yeah, here A, B, C correspond to those measured in the 3 stages showing to the left. Yeah. Yeah, you can see here. And this is for the position A. Yeah. Yeah. Like yeah, this is one and two. This is position A, and it has a electric dipole, and the atrial depolarization. Then you can have the position A, and then here this is position B. Position B, you can see this in this situation, the staple like depolarization. You can see in this position A, the atrial like depolarization. Yeah, so like here, this is the negative, this is the positive, and then you can have the from here to here, there are some like difference. Yeah, and for the position B, and the spectral like depolarization. So here is negative, here is positive, yeah, negative, positive. From the the difference between V2 and V1 is negative. Yeah, it's point B. Yeah, and then for the position C, like the ventricular depolarization. Yeah, this one. Yeah. Okay. Yeah, and here is the positive, here is the negative, and you can see the V2 and the V1 is positive. Yeah, and this is the difference for the C. Yeah, so this is 3 different positions, and for this 3 different positions, there are 3 different like electric potential difference, and then you will know like how the heart beats. Yeah, that makes sense to you. Yeah, this is we use the electric potential to measure our human body's heartbeat and to see if our heart's condition is good or not. Okay, let's talk about more. Let's talk about the other topic like capacitance and the capacitors. Yeah, actually here is an example like about the capacitors and capacitance. You can review it after this class. Okay, yeah. A capacitor, actually we have already talked about capacitor in last class. Yeah, a capacitor is formed by 2 conductors with equal but opposite charge. You can see we talk about conductors last class. Here is 2 plant, and this is positive, this is negative, and then they form a conductor. Yeah, form a capacitor. Those 2 conductors form a capacitor. The 2 conductors are the electrodes or plates. Yeah. Capacitors can be used to store charge, making them invaluable in all kinds of electronic circuits. Yeah, actually, yeah, if you learn like a electronics class or electronics class, and you will know like capacitor is a very often used components. Yeah. In a capacitor, the electric field strength E and the potential difference delta V. Okay, this is just a capacitor voltage potential difference increases as the charge on each electrodes increases. I think this makes sense. If you increase each each electrons, yeah, in this plant you increase it, in this plant you increase it. The electric field strength and the potential difference is increased. Yeah. This makes sense. I'm right. Okay, let's talk about continue talk about the capacitance and capacitors. In a capacitor, the electric field strength E in the different potential difference delta V increases as the charge on each electrodes increases. You can see here. There is a small amount of positive charge is moved from one electrodes to the other. You can see from one to the other, and the electric fields and the potential difference are small, very small. Yeah, because there is a small amount of positive charge. Yeah, and more charge is moved from one electrode to the other. If there is more, yeah, you can see add more, add more. The electric fields are potential difference increase. Yeah, actually this is just how it increase, because there are more charge. Yeah, there are more charge, which means the difference, yeah, is more. Yeah, it makes sense. And correspondingly, the E equal delta V divided D, and then it will this increase, this also increase. That makes sense too, because the D is the same thing. And why is voltage difference is increased, because you add positive charge here, you add a negative charge here, which means the difference will increase. Yeah, that makes sense to you. Okay, the potential difference between the electrons is directly proportional to their charge. Yeah, stated another way, the charge on capacitor is directly proportional to the potential difference between its electrodes. You can see here. This is the charge of capacitors, and this is the capacitance, and this is the difference, electrical potential difference. Yeah, so you can see the potential difference equal what? Q divided C, right? It's directed to their charge. Yeah, directed potential to their charge. If the charge is increased, and then the difference will increase. It decrease. Yeah, the charge difference will decrease. Yeah, the similar. Yeah, then you can get this equation like a Q equals C delta V C, which means the charge on capacitor with the potential difference delta V VC, and the charge on capacitor is directly proportional to the potential difference between its electrons. Yeah, it's easy to understand. Am I right? Yeah, and here, this C actually is a constant of proportionality. C, it is we call it a capacitance. Yeah, for a fixed capacitor, the capacitance is it will not be changed. Yeah, the SI unit, like international unit, capacitance is farad. Yeah, and 1 farad equal 1 F. Yeah, we just use F to represent it, farad, equal 1 coulomb per volt. You can see because the C equal what? Q divided delta VC. Am I right? Q, which means the unit is coulomb, and the V, the unit is volt. So which means this unit is C per volt. That makes sense to you. Okay. Capacitance depends on the shape, size, and the spacing of the two electrodes. Yeah, like I said, if there is a capacitor, there is a existing capacitor, it had already fixed. Is everything is fixed, the shape, size, and spacing of the two electrodes. So the capacitance will be fixed. Yeah, for specific capacitor, yeah, the capacitance is fixed. A capacitor with a large capacitance holds more charge for given potential difference than one with a small like a capacitance. I think this one is easy to understand. Yeah, because you can see the Q equals C delta Vm, right? Yeah, and if you like a large, if this one is a large, yeah, which means the you can hold more charge, yeah, for a given potential difference. If this one is fixed, if you like if a large capacitor means you can hold more charge, yeah, than one with small capacitance. If that makes sense to you. Okay, let's talk about the charging a capacitor. Yeah, to charge a capacitor, we need to move charge from one electrode to the other. The simplest way to do this is to use a source of potential difference, such as a battery. Yeah, a battery uses its internal chemistry to maintain a fixed potential difference between its terminals. Yeah, if you want to charge a capacitor, you can use a battery. Yeah, and this battery uses its internal chemistry to maintain a fixed potential difference between its terminals. Okay, this is like how to charge the capacitor. You can see, yeah, this is the direction of charge motion from here to here, and you can see the charge flows from these electrodes, leaving it negative. Yeah, charge flows from this is it, electrodes, leaving it negative. Yeah, you can see, which means the positive, the charge will flows from this and leaving this negative, and then the charge then flows through the battery. Yeah, which acts as a charge pump. And then the charge can move freely through the wells. And, uh, and the charge ends up on these electrodes, making it possibly charged. Yeah, which means if you connect a voltage, a battery here, and then all the positive charge will flow from here through the battery and go to the positive plate, and left the more negative here. That makes sense to you. So which means the difference will bigger. The different potential difference will bigger. Okay, that makes sense to you. Okay, then you can see the moment of charge stops when the potential difference is equal to the battery voltage, the capacitor is then fully charged. Yeah, you can see if the difference is equal this one, which means there will be no like uh, difference here. So there will be no like a charge flows. Does that make sense to you? Okay, and then if the battery is removed, the capacitor remains charged. Yeah, with if the battery removed, yeah, the capacitor remains charged with the delta, like the difference potential still equal to the battery voltage. Yeah, which means after you remove the battery, and if you didn't connect something to this well, this is just storage this charge and keep this situation for a long time. Yeah, so which means that a capacitor can be used to store charge. Does it make sense to you? After you remove the battery, and this potential difference will remains. Yeah, it will remains charged. Yeah. Okay. Okay, let's talk about this question. What is the capacitance of these two electrodes? Yeah, we know like the Q, we know the equation like Q equals C delta V. So which means this question let us to calculate the capacitance. Capacitance equal what? Q delta V. Yeah, for the Q, it's just like a 4 multiple 10 power negative 10 see, yeah, for the voltage difference, yeah, it is 2 volt here. Yeah, so which means it equal what? For this one divide it means 2NF. Yeah, so the answer should be this one. Yeah, you use this equation to calculate it. Yeah, that makes sense to you. Okay, let's talk about this example. Yeah, 1.3 μF capacitor is connected to a 1.5 voltage battery. What is the charge on the capacitor? Actually, I think this one is easy for you. Yeah, charge flows through the battery from one capacitor electrodes to the other until the potential difference delta Vc between the electrodes equal that of the battery or 1.5 volt. Am I right? So which means the difference should be 1.5 volt. And yeah, we should use the equation like Q like Q equal what C delta V. Am I right? So yeah, the charge on capacitor is given by equation 21.18. Yeah, it's just this equation. Yeah, and then here we know the C and we know the potential difference, and then we can calculate the charge on the capacitor. Yeah, you can see the charge on the capacitor is this one. And the small charge is expected for the small capacitors. Yeah, because you can see the capacitance is very small. So the charge is small and the small voltage. Does that make sense to you? Okay. Let's talk about the parallel like a plate capacitor. Yeah, a parallel plate capacitor is important because it creates a uniform electric field between its flat electrodes. Yeah, we have already talked about the parallel plate capacitor creates a uniform electric fields between its flat electrodes. Yeah, the electric field of a parallel plate capacitor is equal this one. We have already talked about in last class. Yeah, how to calculate the electric fields of a parallel plate capacitor. Yeah, this is the charge, and this is a constant, and this is the area. Yeah, do you remember that? Okay, A is the surface area of the electrodes, and Q is the charge on the capacitor. Okay, in the electric field strength of the parallel plate capacitor is related to the potential difference delta Vc. Yeah, and plate of space D by this one. Actually, this is we talk about in last class, the electrical field strength of a plate capacitor. Yeah, we can use this equation to calculate it. Yeah. Yeah, and comparing the difference equation describing the electric field of parallel plate capacitor, we found, yeah, we have this equation. Yeah, and we also have this equation. Yeah, in last class. And then we just, because those two are same, so we just let these two equal with each other. And so then we can get this equation. You can see here, you just put this two here, and then it will equal. Yeah, that makes sense to you. Okay. And if we compare the previous equation to the definition of the capacitance, we see that the capacitance of the parallel plate capacitor is, yeah, because we know like the Q equals C delta V. Am I right? So C equal Q delta V. And here you can see Q equal this one. This part, am I right? So you just put and C C equal, yeah, you know Q equal what? This one, am I right? So A divide what? Yeah, try to remember it, and let me put it here. Yeah, try A and D delta V C and divide delta VC. So which means the delta VC will be removed and it will equal this one. Am I right? So this is the capacitance of a parallel plate capacitor. It's related to the area plate area A and separate D is not related to the potential electrical potential of the charges. Yeah, which means the capacitance just like depend on the size and the distance. And yeah, that makes sense to you. Okay, let's talk about this quick chat question. A capacitor has a charge Q. The plates are then pulled apart so that the distance between them is larger. Yeah, D increase. After the plates are pulled apart, yeah, which one is right? Actually, this one is a little tricky. Yeah, you can see this is like a isolated like a capacitor. Yeah, so which means the charge will keep same always because there is no outside battery or like a source to give it more charge. So the charge will like keep same always. And so we have this equation like E equal Q. Yeah, so like because the charge keeps same, so which means this one is now like will is now changed. So the electric electric field is also like keep same. Yeah, so which means the charge and the field remain constant. Yeah, that makes sense to you. But what is changed here? You can see because delta V equal Q divide C, and right? Equal what? Equal Q D A. Yeah, because the D is larger, so the voltage difference is the like electrical potential difference is large. So which means the potential electrical potential changed, but the charge and the field remain constant. Yeah, so pay attention to this one. Yeah, this one is a little tricky. So the right answer is E. Okay, let's continue to check the other one. Yeah. The capacitor is attached to a battery. The plates are then pulled apart so that the distance between them is larger. Yeah, so this one, yeah, you can see the difference between this one and the last one is there is only isolated capacitor, but here there is a battery. Yeah, so which means the like so there is a battery, so which means the Q equal what? Yeah, let's check. Let's write it down the equation here. The Q equal this one A D V. So which means this one is like an increase. So the Q will decrease. That makes sense to you? The charge will decrease, and the field, yeah, field equal what? E equal delta V D. So this one is increase, so this one is decrease. Yeah. So which means the answer is D. Yeah, does it make sense to you? Yeah, because this is the difference between this one and the next one. Yeah, there is a battery, which will like the voltage difference will be the same. Yeah, because it always connect to the battery, which means the difference always the delta V keeps the same. You call this difference, the difference for this battery. Yeah, so the voltage difference is keep the same, and since the distance become larger, so the E is also the charge the field will decrease and the charge also decrease according to the equation. Yeah, that makes sense to you. Okay, let's continue to talk about this example problem. And a parallel plate capacitor is constructed of two square plates. Yeah, you can see like similar like these two square plates, and 1 meter on each side. Yeah, like a 1 meter. This is a square, so 1 meter, 1 meter, 1 meter, and the separated by a 1 millimeter gap. So the millimeter gap D equal 1 millimeter. what is the capacitance of this capacitor? If we charge to 100 volt, how much charge would be on the capacitor? Yeah, we know like the equation. Yeah, just write down the equation. C equal this one A divide D, and here this one is the constant value, and this is just like a square, the area of this square, and this is the distance. Then you can calculate the C, am I right? So like so you can calculate the capacitance of this sensor. If we charge to 100 volt, so Q equal what? Q equal this one. Yeah, actually Q equal, we can use the simple equation. Q equal delta V D. Yeah, the delta V, yeah, equal 100, am I right? And then D is 1 millimeter. Yeah, so you can calculate the Q based on this equation. Yeah, so I will leave this to you to like leave this to you, let you to calculate by yourself. If you have any question, just let me know. Okay, let's talk about the other example, like making a parallel plate capacitor. Yeah, the capacitance of practical parallel plate capacitors is quite small in the PF range. Yeah, it's PF range. Do you know PF range is how small? Yeah. Do you know that? Try to think of. Yeah, actually the PF range is 10 power negative 12 F. Yeah, it's around like this. It's very, very small. Suppose you want to make a 1 point mu F capacitor using square plates separated by 1 millimeter. How large do the plates need to be? Yeah, like yeah, we know the capacitance depends on the area and the spacing. We know the capacitance and the spacing for now. Yeah, the capacitance is here and the spacing is here, so we can determine the area. Yeah, the area of the plates is the square of the edge length. Yeah, this area is just the square, the edge length. Yeah, we know that. Yeah, for the square. Okay. Yeah, regarding rearranging equation 21.2, yeah, we solve the area of the planes. Yeah, the 21 is just like C equal what? C equal this one A D. That makes sense to you. So which means A equal D C and A equal what? L square, right? So then we call this equation. And here, this is D, and this is the capacitor, and this is the constant, yeah, permitted, okay, constant, if you remember that. Actually, you don't need to like memory this value. You can check it like when you calculate it. And the final length is 11 meter. Yeah, let's assess this result. To achieve this value of capacitance, you will need two conducting plates more than 55 feet on a side separated by 1/25 inch. This isn't really practical actually, but this result is expected. The problem statement noticed that practical parallel plate capacitors have a much smaller capacitance. Yeah, like you can see here, the capacitance is just this value. It's quite small. Yeah, even like the like area is very big. Yeah, and yeah, to obtain a reasonable value of capacitance, we need a large electrode area and a small separation. Yeah, we need a large electrode area and a small separation. In practice, this is accomplished by having large foil electrodes separated by a thin layer of isolator. You can see here, here are some like thin layer of isolator, and This one is just some large foil electrodes. Yeah, and this construction makes it possible for large electrodes with a small separation to be squeezed into a small package. You can see you can squeeze it into a small package. Yeah, like an isolator consists of vast numbers of atoms. When an isolator is placed in an electric field, each atom polarizes. Yeah, polarization occurs when an atom's negative electron cloud and positive nucleons shift very slightly in opposite directions in response to an applied electric field. Yeah. An induced positive charge builds up on one surface of the isolator, and an induced negative charge builds up on the other surface. Yeah. Here we talk about the dielectrics and capacitors. You can see here we talk about the structure of the parallel like plate capacitor, and then we talk about how these practical capacitors work. You can see here uh, because like the isolator, yeah, you can see the isolator um, like it can separate the large foil electrodes, yeah, and make it uh, have the enough capacitance, yeah, and this is the reason why it can work. You can see here is a positive nucleon shift very slightly into the direction of the field. And this is the direction of the field, yeah, and the positive nucleon shift very slightly into the direction of the shift, and the negative electron clouds shift very slightly in the direction opposite opposite the field. So this will be electron, and this will be positive nucleon, like a proton. Yeah, because of polarization, this surface has an excess of a positive charge. Of course, because the positive will shift to this direction, and this surface has an excess of negative charge. Yeah, that makes sense to you. So this polarization occurs when an atom's negative electron cloud and positive nucleus shift very slightly in opposite directions in response an applied electron field. Yeah, an induced positive charge build up on one surface of the insulator, and an induced negative charge build up on the other surface. Yeah, this is just the process of dielectrics. Yeah, okay. The induced charge on an insulator will create a uniform electric field, like in a parallel plate capacitor, but one that is directed opposite to the applied electric field. A dielectric is an isolator placed between the plates of a capacitor. A capacitor's electric field paralyzes the dielectric. The dielectric creates an electric field of its own opposite the capacitor's field. The two fields add to give a net field in the same direction as the applied field, but smaller. Thus, the electric field between the capacitor plates is smaller with a dielectric. Yeah, this is how the dielectric works in this kind of capacitor. And you can see this is this is a capacitor, and this is a negative plate. This is a positive plate, and this is applied field from charge on capacitor. Yeah, field due to induced charges on dielectric. Yeah, you can see. because of the dielectric, and some positive is here and negative is here, which means the positive will be smaller, the negative will be smaller. Yeah, and this we call the dielectric. And these charges, we call it induced charges. The net electric field is a vector sum of the applied field and the field due to the dielectric. Yeah, you can see this is the original electric field, and this is some dielectrics, and yeah, this brown one dielectric field, and then the net electric field is a vector sum of the applied field and the field due to the dielectric. And yeah, when a dielectric is inserted, the electric field between the plates decreases, which implies the potential differences decreases as well. We talk about that the electric field increases, the potential difference will increases. If the electric field decreases, and the potential difference will decreases as well. If the charge remains the same, the capacitance, yeah, is this one. Yeah, since the charge remains same, but the potential difference decrease. So which means the capacitance increase. That makes sense to you? Yeah, the presence of dielectric results in an increased capacitance. Yeah, the dielectric constant K of the material determines the factor by which the capacitance is increased. Yeah, this is K. This K is different with the K we talk about, calculating the electrical field. Yeah, and yeah, so it's a different thing. It's just called dielectric constant. Yeah, and this is the original one, and this is original capacitance, and this is after insert dielectric. And then this is a new capacitance. Yeah, this is capacitance of parallel plate capacitor with a dielectric constant K. Yeah, C0 is a capacitance without a dielectric present, which means that this is the original one. Does that make sense to you? Yeah. And yeah, this is just since we want to increase the capacitance for capacitor. Yeah, there is a one technology called dielectrics. It's dielectrics, and it's just insert an isolator. Yeah, generate applied field. This applied field can this applied field will decrease the original electric field, and then the net electric field. Since the potential difference and decrease, so the capacitance, the charge remains the same, then the capacitance increases. Yeah, that's the theory behind that. And then this is the equation for the new capacitance based on the original one. Yeah, that makes sense to you. Okay, let's continue to talk about this. And this is dielectrics and capacitors. Yeah, some dielectric constants of some material at 20 degree. Yeah, and you can see if the dielectric material is vacuum, and it's just dielectric constant K is just a 1. It just means if you put a vacuum insert vacuum in as an insulator in the capacitor. Yeah, it's the same thing. It's the same with the original one. If you put air, it is 1.0005554. Yeah, it's just similar to vacuum, which means if you put air, yeah, it's just similar with very close to the original one. So we just use 1 in our calculations. And this is a Teflon, and it is 2, and this is paper. You put paper 3, and some like a Pyrex glass. It's 4.8. Yeah, which means this C0 is the original one, and for the vacuum, it just the new is new equal like original one. This is like approximately original one, and this is just 2 times original one. This is 3 times original one. This is 4.8 original one. This is 9 original one. Yeah, this is yeah, as a cell membrane and ethanol and water and strontium tinate. Yeah, it is 300. Yeah, so which means if you want to increase the capacitance for one capacitor, you can insert this material inside the capacitor and to increase the capacitance. That makes sense to you? Okay, let's talk about one example, finding the dielectric constant. A parallel plate capacitor is charged using a 100 volt battery, which means like potential difference is 100 volt. Then the battery is removed. If a dielectric slab is slid between the plates, filling the space inside, the capacitor voltage drops to 30 volt. What is the dielectric constant of the dielectric? Yeah. Let's talk about the strategy. After the capacitor is removed from the battery, the charge on the plate doesn't change. Yeah, the field between the plates is reduced by the presence of dielectric, so the voltage decreases. Yeah, we will use the decrease in voltage to determine the dielectric constant. Okay, that's the basic definition of capacitance. Equation 21.80 relates the charge to the voltage and the capacitance. Just the Q equals C, like delta V C. Yeah, this is the equation 21.18. And the initial charge Q1 is the same as the charge Q2 after the dielectric is inserted. Yeah, so we have this one, the Q1 equals C, like the difference VC1, and the Q2 equal the C2 delta VC2, and inserting the dielectric increases the capacitance by a vector of K, so that C2 equal K C1. Yeah, that makes sense to you? Okay. Since thus like this one equal this one, because we know like C delta V C1 equals C2, this C1 C2 delta V C2, and like C2 equal K C1. So then we got C1 delta V C1 equal K C1 delta V C2. Yeah, that makes sense to you? Okay, yeah, we got this equation. And like you can canceling C1 delta V C1. Yeah, because C1 delta is like equal K delta VC. Yeah, because you can see here C1 delta VC equal K K C1 delta VC. Yeah, because so you can see from this equation, yeah, we got a K equal what? C1 delta V C1 divided C1 delta V C2. And C1 removed, so which means K equal delta V C1 divided delta V C2. Yeah, that makes sense to you? Yeah. and VC1 equal 100 volt and VC2 equal 30, which means the K equal 3.3. Yeah, the voltage goes down by a factor of approximately 3. So we expect a dielectric constant of approximately 3 as we found. Yeah, that makes sense to you because it dropped 3 times. Yeah, by a factor of approximately 3. Yeah, that makes sense to you. Okay. Let's continue. Let's talk about this example problem. Yeah, a parallel plate. Let me read it for you. A parallel plate capacitor with a capacitance of 200 PF is charged to 100 volt. Then the battery is removed. A sheet of typhon like is 2.0 is then slid between the plates. By what factor does the charge on the plates change? Actually, and the other question is, what is the final potential difference between the plates? Yeah, we know once the battery is removed from the capacitor, the charge on each plate is fixed. Yeah. So inserting the signal typhon changes capacitance, but there is no source of additional charge, so the charge on the plate remains unchanged. That makes sense to you. Yeah, we know Q equal what? Q equal CV. I'm right. This is equal C is this one, 200 PF, like a 10, like a multiple V, like a 100 volt. Yeah, this is the charge, and the charge will remain same. And then the new capacitor is because this is K equal 2. So the new C new equal what? K C equal what? Equal like a 2 multiple 200 PF equal 400 PF. Am I right? So which means the V equal so uh the factor should be what does and C, because new C does the charge on the plate change, which means the charge will not change because once the battery is removed from the capacitor, the charge on each plate is fixed. Yeah, so which means it is 1. Yeah, the charge will not change. And for the final potential difference, yeah, V, you can see V equal what? V equal QC. Q is the same thing, this one. Yeah, and the C is just the two, like multiple two to the original one, which means 200 blah 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 1 divide 400 blah blah blah, which means you just divide 2 to 100, which means it is 50 volt. Does it make sense to you? Okay, let's continue. Yeah, you can calculate it by yourself, and I just give you the hint. Okay, let's talk about the energy and the capacitors. Yeah, a charged capacitor stores energy as electric potential energy. Yeah, the potential energy, yeah, V like a capacitor, stored in a charged capacitor is this one. We just use this equation to calculate it. Yeah, Q delta V. Yeah, this is equal this is the average difference, and the average difference just half, like the difference. Yeah, yeah. Since Q equal this equation we just talk about, the electrical potential can be written this one. Yeah, because VC equal this one and Q equal this one, which means 2C delta VC, and which means the electrical potential energy in the capacitor with charge Q and the potential difference. This is the relationship between the electric potential energy and the charge Q and the potential difference delta Vc. Yeah, that makes sense to you. Okay. And let's talk about this example problem. And the capacitor bank used to power a large electromagnet is charged to 23,500 volt and stores 8.5 megajoule of energy. What is the total capacitance of the capacitor bank? Yeah, actually we can use this equation. This here, this equation. I just write it down here. Yeah, C equal like half C delta V C square. Yeah, because you can see the capacitor bank used to power to this one. So which means the difference is the potential difference is this one. I'm right. And the storage this one 8.5 mg. This is the potential energy. Yeah, electric potential energy, which means it is mg equal to half c and square. Yeah, you can use this equation to calculate the capacitance of the capacitor bank. It does make sense to you. Yeah, if you have any question, just let me know. Okay, let's talk about the other example, finding the power delivered by a capacitor. Yeah, a camera flash uses a capacitor to make a very bright but short duration pulse of light. Yeah, I think everyone use the camera flash before. I'm right. Actually, what's the theory behind that? Actually, the camera flash use a capacitor to make a very bright but short duration pulse of light. A typical external flash unit has a 220 mF capacitor charged to 330 volt. When the flash is triggered, the capacitor discharges in a time of 1 milliseconds. What's the power delivered to the flash lamp? Yeah, we will find the energy stored in the capacitor and then use the energy and the discharge time to find the power. Yeah, does it make sense to you? Okay, we know the voltage and the capacitance. Yeah, so we can find the energy stored in capacitor using this equation. Yeah, because we know the voltage and we know the capacitance, and then we can calculate the energy stored using this equation, and it is 12G. 12, this is a good deal of energy, and given the short time, the power is large indeed. Yeah, the power equal what? The power equals the like electric field. Yeah, divide it's the power is just a short time. The electric field change. Yeah, it is just okay. I think this one is just is a little mistake. The P equal what? The power is just the energy stored in a short time. Yeah, because we know the capacitor discharge in a time of 1 millimeter, which means this storage just charge in 1 millimeter. So this is it should be VUC. Yeah. So which means UC divided delta T equal this one divided this one, and then we can get the power is 12,000 watts. Yeah, this is a lot of power, but we know that the flash is very bright, so our result makes sense. Yeah, just this is a typo. Yeah, and I will modify it later. Okay. Okay, let's continue talk about the energy and capacitors. Yeah, a capacitor can charge very slowly and then can release the energy very quickly. Yeah, this is an example. I think we saw this before in TV series or some video. Yeah, a medical application of this ability to rapidly deliver energy is defibrillator. Yeah, defibrillator is a state in which the heart muscles twitch and cannot pump blood. A defibrillator is a large capacitor. You can see if you observe it very carefully, it has a two layer. One is positive like plate, one is the negative plate. Yeah, this is a large capacitor. Yeah, it's usually if you do some experiments in physical lab, and the capacitor is very small. Yeah, it's very small. Yes, this capacitor is quite big. Yeah, a large capacitor that can store up to 350 joule of energy and release it in 3 milliseconds. The large shock can sometimes stop vibration. Yeah, that makes sense to you. Yeah, it's just like this big energy. Yeah, why the capacitor can like can like do these things, because a large capacitor can store much energy, and this energy can release in a very short second, and this large shock can sometimes stop fibrillation. Yeah, but just notice sometimes, not always. So sometimes if you find the nurse or the doctor use the capacitor but it doesn't work, yeah, it mm, which means like the fibrillation, yeah, cannot be like stopped by this kind of shock. Yeah, it can, it sometimes it works, but sometimes it cannot. Yeah. Okay, let's talk about the energy in the electric field. Yeah, the energy stored in the capacitor, we talk about it, that it is equal this one, am I right? And then the C, the capacitance can be represented in this equation. We talk about before in this class. Yeah, and the difference, the potential difference, yeah, it equal this one. So then we can use this equation to calculate like energy stored in the capacitor. Also, yeah, you can see here is the electric field, and then this is the capacitor area. This is the distance, and this two is a like a constant. Yeah, which means the energy is stored in the capacitor's electric field. Yeah, which means, yeah, you can see this energy related to the electric field. Yeah, the capacitor energy is stored in the electric field in volume AD between the plates. Yeah, that makes sense to you. Okay. Yeah, because of the quantity AD, the volume inside the capacitor is the volume in which the energy is stored. We can define the energy density UE of the electrical field. Yeah, UE is energy stored and volume in which it is stored. Yeah, you can see from this equation we know that yeah, we know that yeah, E from this equation, like we know like the we can define the energy density UE. Yeah, this is just a definition for the energy density. Yeah, energy density UE we can uh, is equal what energy stored is UC, and the volume in which it is stored. This is AD. Yeah, volume means, yeah, because you can see this is the A is the area, and right, D is the distance. This one and this one multiple, it is just the value of this capacitor. Yeah. Okay. The energy density has a unit joule per uh, cube meter. We first introduced electric field as a way to visualize how a long-range force operates. Yeah, but if the field can store energy, the field must be real, not merely a pictorial device. Yeah, we talked about this before. Yeah, because we know like the field cannot be seen, but the field it is real. Yeah, that makes sense to you. Okay, let's talk about some quick check question. A capacitor charged to 1.5 volt storage to mg of energy. If the capacitor is charged to 3 volt, it will store. Yeah, we know like here. Yeah, we know this equation. Yeah, which means UC equal half what? Half C V C square, and then a capacitor charge if the this one is 1.5 volt, and then it stores 2 mg, and we can calculate the C, am I right? Here, if capacitor charged to 3, which means this will become like from 1.5 to 3, it will be multiple, which means but here is square, so which means it should be like 4 times, yeah, that compare with the original one, so which means it should be 8. That makes sense to you? Yeah, because here it increase twice, and here is a square, means it will be 4 times. Yeah, that makes sense to you? Yeah, because you can see the UC depends on the square, the voltage distance square. Okay, let's talk about this example, finding the energy density for a defibrillator. Yeah, I think I just put this. Yeah, this is just should be removed. A portable defibrillator unit contains a 150 mAh capacitor that is charged to 2000 volt. The capacitor plates are separated by a point 0.0 millimeter thick dielectric with K equal 300 K 300. What is energy density in the electric field when the capacitor is charged? How much total energy is stored in the capacitor? Yeah, we can use the equation we talk about to calculate those two. Yeah, we will model the capacitor as a parallel plate capacitor with a dielectric between the plates. Yeah, and to find the electric density, we need to know the electric field between the capacitor plates. Modeling it as a parallel plate capacitor, we can find the field with equation 21.7. This equation, yeah, E equal delta V divided D, and we know the voltage difference. It is 2000, and we also know the distance. Yeah, it has already give you. Yeah, this is the distance by the. Yeah. And yeah, this is the voltage difference, and this is the distance. Yeah, does it make sense to you? So we can calculate the electric field, and then with the electric field in hand, we use the equation 21.25. Yeah, this actually, yeah, this equation to find the energy density. Let me show it to you. Yeah, this equation we can use. Yeah, to calculate the density, energy density. Yeah, and then yeah, we know the key. This like a ellipse. There ellipse is a constant. Those two are constant, and this is what we have already got. Yeah, and the k is 300. We know that. Yeah, and this is another constant, and this is what we calculate, and this is the final energy density. Yeah, 5.3 multiple 10 power 7 g per cubic meter. Yeah, actually the total energy stored. Yeah, we know that we can calculate it using this equation. Actually, the total energy is equal this equation, and we know the capacitance. Yeah, here is the capacitance, and we also know the voltage difference, and then we can calculate the total energy stored is 300 joule. yeah, the electric field is quite large, larger than the field that would cause a spark in air. But a large field is needed to store a good deal of energy. The energy density is large, as we'd expect for a portable device, and the total energy stored is of the correct order. So our results are reasonable. Yeah, because you can see, uh, for this result, the electric field is large, but the electric density is also large, and the energy stored is also large. So it constants. Yeah, that makes sense to you. Okay. Yeah, this is what we talk about in today's class, and we mainly focus on parallel plates and potential and the relationship between potential and the fields. Yeah, and there are some equations you can like calculate it like based on the given information. Yeah. Okay, let's do a summary for this chapter. Yeah, chapter 21. Yeah, you can view some videos for that. Yeah, for this chapter, and I will not play it in this class. Okay. Yeah. Uh, Firstly, let's talk about what we talk about. This is the thing we talk about in last class. Yeah, electrical potential and electrical potential energy. You can see the electric potential like V is created by charges and exists at every point surrounding those charges. Yeah, there are some charges. The electric potential V exists no matter if there is a charge around it. That makes sense too. When a charge Q is brought near these charges, it acquires an electrical potential energy. Yeah, and this is the equation for electrical potential energy, Q V voltage. Like at a point where the other charges have created an electrical potential V, energy is conserved for a charged particle in an electrical potential. Yeah, we talk about the electrical potential energy and the conversation of electrical potential energy. Yeah. In a word, the final kinetic energy plus the final electrical potential energy equal the initial kinetic energy plus initial electrical potential energy. Yeah, and you can see this equation can become this equation. Yeah, we can use this equation to calculate the how the uh, energy is changed. Yeah. Okay. And then we talk about some sources of potential, like a potential difference, like the voltage, also we call it voltage difference, like the delta V, are created by a separation of charge. Yeah, because you can see a battery, uh, there is a battery because there is positive is negative and positive negative is separated and then created a like potential difference. Two important sources of potential difference are one is battery. Yeah, we talk about it. Use chemical means to separate charge and produce a potential difference. And the other one is opposite charges on a plate of a capacitor which created a potential difference between the plates. Yeah, there are two different important source now to create a potential difference. And the electric potential of a point charge Q, yeah, you can use this equation to calculate. And also for the plate of a capacitor, you can also use an equation to calculate it. And do you remember what is it? Yeah, try to think about that. I will give you several seconds. Yeah, it is like a V equal Q divide AX. This is a charge, and this is a constant, and this area, this is like a position, where is the charge in what's the location for this charge? Yeah, so uh, this is what we talk about in the first class for this chapter. And then we in today's class we talk about the connecting potential and field. You can see actually the electric field is everywhere perpendicular to the equipotential surface. Yeah, this is the direction of decreasing potential. Yeah, and the electrical field points downhill in the direction of decrease in V, which means this is the direction of decrease in potential. The field strength like is inversely proportional to the distance d between the equipped potential surfaces. Yeah, we talk about in this class. Yeah, you can review it. Yeah, and for a conductor in electrostatic equilibrium. Yeah, there are some like features. Yeah, we talk about only there are five. And this is the last one is we add in today's class. Yeah, like the any excess charge is on the surface. The electric field inside is zero, and the exterior electric field is perpendicular. Yeah, you can see perpendicular to the surface, and the field strength is largest at the sharp corners. The entire conductor is at the same potential, and so the surface is at equipotential. Yeah, the surface is at equipotential, which means every point in the surface has the same like electric potential. Yeah. This is like the graphical representations of the potential. Like as like a distance increase, the voltage will like increase. The voltage will like decrease. Yeah, and this equipotential surfaces. And this is it will like this is equipotential map. Yeah, it is a positive like this is just equipotential map. In the middle it is like the electrical potential it is the largest. Yeah, like the when the distance is a small the voltage is large. Yeah, so as the distance increase and the voltage the electrical potential decrease. Yeah, that makes sense to you. Okay. Yeah, we also talk about the capacitors and the dielectrics. The charge you can positive and negative Q on two conductors, and the potential difference this one between them are proportional. Yeah, this is the equation we talk about today. And here here is C is the capacitance of two conductors. A parallel plate capacitors with place of area A and separate D has a capacitance. This one, yeah, we talk about this in today's class and how to like add this equation, which means that the capacitance only depends on the area and the distance. This is a constant. Yeah. Okay. Yeah, for like when a dielectric is inserted between the plates of a capacitor, its capacitance is increased by a factor K. Yeah, actually, yeah, this K is a constant. The dielectric electric constant of the material. Yeah, for one specific material, this K is fixed. The energy stored in a capacitor, you can use this equation to calculate the energy stored. And the energy is stored in the electric field, which has a energy density. This one, yeah, we can use this equation to calculate the like energy, the energy density. And this key is a constant. Yeah, is a dielectric constant of the material, and this is the constant like a permitted constant, and this is the electric field. Yeah, you can use this one equation to calculate the electric density. Yeah, and for capacitor charged to like delta Vc, the potential at distance x from the negative plate is this one. Yeah, we talked about just now. Yeah, this equation. Yeah, this equation. If you can be also write as this equation. Yeah, and this x is the d is just the total distance, and the x is just some place in between this capacitor. Yeah, and this is the some place. For example, here this is the x. This is the x, and this is the d, and this is the difference from the negative to the positive difference potential electrical potential. Yeah, and this is the point. This point like electric potential in this point. Yeah, the electric field inside is using this equation to calculate. And there are some units that electric potential. Yeah, is this unit electric field? You can use this like a unit and energy. Yeah, you use these things. Yeah, is a kinetic energy gained by an electron upon accelerating through a potential difference number 1 volt. We talk about this in last class. You can review it if you want. Yeah, this is the like main things we talk about in this chapter. Yeah, hope you understand like what. Yeah, last chapter we talk about the for electric force, electric atoms, and some information related to those. And this chapter we mainly focus on electric potential and electric field. Yeah, you can see it has some relationship, and actually even you cannot see it, but they are there, they are real. Yeah, okay. Yeah, this is what we talk about in this class. And if you have any question, just let me know. Okay, bye, see you.